This is a updated version of a presentation given to the Nreca T&D Committee in 2018. The low voltage regulation technology we are describing today is the culmination of 20 years of development and operation on utility grids around the world. Our first model was produced for the Bonneville Power Administration Distribution Efficiency Initiative study. From that, Scottish Power heard about our technology and we produced 150 regulators for them to mitigate voltage compliance problems caused by wave generation stations on the North Sea. And from that, Ergon Energy in Australia heard about our technology, and we eventually installed 2,000 regulators on their single wire earth return systems in the outback of Australia. Today we are discussing a 50 kVA residential low voltage regulator which operates on the secondary side of the distribution transformer. In North America, utilities would call this a single-phase service, although more correctly, the regulator is a split-phase design for a three-wire service. The LVR50 has true subcycle regulation. It creates no total harmonic distortion. It will operate with an input voltage range between 160 and 300 volts. It provides a plus or minus 8.3% correction, which is nominally plus or minus 20 volts. It is designed to have a 20-year mean time to failure. It's also designed for 50 degrees C ambient rating. At 426 amps, it will go into an overcurrent bypass, which automatically resets when the current drops to more normal. It has no limits on the load power factor, meaning it will regulate a totally capacitive load or a totally inductive load. It has bi-directional regulation to support distributed energy resources. It also has programmable bidirectional line drop compensation. In general, the value of this technology is to mitigate voltage problems, either high or low, which are caused by the impedance of the circuit. Typically, the use cases fall into three categories: power quality, voltage compliance, and supplemental support of voltage optimization or CVR programs. It's important to note that smart meter data is moving the voltage compliance point of judgment from the medium voltage substation to the low voltage meter. So power quality applications include mitigation of flicker, sags, and swells. It can be used to balance three-phase voltages for unbalanced motors. It can be used to compensate for the open delta services where the phase angles tend to collapse and give you an unequal delta voltage. And in general, it delivers a level of service that otherwise is difficult for utilities to provide. So the regulator will compensate for voltage rise due to reverse power flow on the secondary circuits. It also compensates for voltage drop due to high source impedance on long rural feeders. And it can be selectively applied in CVR programs to maintain compliance for outliers which have too low a voltage. This allows you to lower the medium voltage feeder voltage more than you would otherwise be able to. This chart illustrates the regulation characteristics of the low voltage regulator. The blue line represents an increasing input voltage to the regulator. At about 160 volts, the regulator will turn on and it will start to boost the voltage 8.3%. As the input voltage continues to rise, it will continue boosting as much as it can until the output reaches the set point, at which time the set point will remain constant while the input voltage continues to rise until the dynamic range of the regulator is exceeded. Then it will continue to buck the input voltage, 8.3%, as the voltage continues to rise until it reaches 300 volts, at which point it will shut off and stop regulating. In this strip chart, the red trace is the input voltage to the regulator, and the black trace is the output voltage to the regulator. This blue trace down here is the load amps, which are on the right-hand scale. So you can see the regulator here is dynamically regulating, is bucking the input voltage from about 244 down to 230. In this strip chart, the opposite is occurring. The regulator is boosting the output voltage while the input voltage is lower than the output. So the blue line is the input to the regulator. The red line is the regulator output. And these are 1 minute interval average data points. Many manufacturers claim some sort of sub-cycle regulation in their marketing literature, but the details tend to get pretty vague as you dig into it. We, however, are happy to disclose exactly what we mean. Our regulator changes its duty cycle 20 times every cycle, which means it changes the output voltage 4.3 million times an hour. We can do this without creating any voltage or current total harmonic distortion, and it's fast enough to reduce flicker as measured by the PST value by an average of 66%. In this strip chart, which is half-second interval data, the red line is the output of the regulator and the black line is the input from the grid. You can see a couple places here where the line regulator changed its taps, and here there was an event that caused the regulator to transition from bucking to boosting. We can zoom into that and look at it in more detail because of the high resolution data that is recorded in the regulator. Zooming into the data, we can see that these are actually 4 separate events, and these are the type of events that would cause flicker had we not corrected the output with the regulator. It's a little bit difficult to comprehend 4.3 million corrections an hour. If you look at just one of these events, which lasted 1 second, the regulator made 1,200 adjustments during that 1 second. This helps put into perspective how the regulator can compensate for flicker. This is higher resolution data from a Fluke 1760 power quality meter. The meter plots 1/2 cycle RMS values. So the blue trace is the line voltage during a motor start, and you can see that the voltage dropped 17.7 volts at the beginning of the motor start, and the red line is the regulator output. The regulator output dropped 8.9 volts in the first half cycle, so it was already starting to correct for the change in input voltage. It overshot here slightly in the second half cycle, but essentially the regulator compensated for the motor starting in 1/2 of 1 cycle. To put the flicker reduction in more quantifiable terms, the chart below plots 600 PST values. The PST on the input to the regulator is in blue, and the PST on the output of the regulator is red, and each pair, input and output pairs, are plotted in descending order in this chart. We used to share a distribution transformer with a cabinet maker, and they thoughtfully provided us with many motor starts every day, and that's how we collected this data. So you can see that a input PST value of nearly 3 is reduced to nearly 1. An input PST value of 1 is reduced to about 0.33, and this 60% reduction carries out all the way down as we approach 0. The regulator collects operational data for up to a year. There are 3 types of files. There's a time-stamped fault log. There's what we call 24-hour files, which are half-second interval data, and we store 7 of those. So you can get this data file for the last 7 days. And we also store what we call month files, which take the half-second interval data and derive a 1-minute average value, as well as retaining the minimum and maximum value from the half-cycle data. And there are 12 months of these. At the end of a year, they start to overwrite the month files. The regulator comes with a Bluetooth interface which runs at 38.4 kbaud. It has a range of approximately 150 feet, and we call this the local connection. It's primarily intended to give access to the regulator's operating parameters, the fault log, that type of thing. All the data files are also accessible for download through this interface, but it's painfully slow because the data files are typically quite large. In addition, we offer an open standard serial interface for wide area network integration. We typically don't supply any hardware for this because every utility seems to have their own idea of what the ideal solution is. But it's open standard, and we can help you integrate whatever hardware you prefer into this. The important point is that the regulator is designed to operate autonomously. You are not required to maintain the cost burden of a centralized control system for this to operate. You largely set the set point and forget about it. The regulator has an external control switch which can hold the regulator in a disabled condition, which means the input voltage is equal to the output voltage. When you switch it from pause to regulate, the microprocessor is reset and it boots up and starts to regulate. This gives the installer a known startup condition, and it's helpful for troubleshooting if necessary. The other reasons for this are only applicable to the 50 Hertz world, so we will skip them for now. This drawing describes the mechanical packaging of the regulator. It weighs 125 pounds. It's about 21 inches wide and 20.5 inches tall. Typically, these regulators are installed by servicemen, and they don't need a crane and a line crew for installation. This is a one-line diagram of the LVR50. The core of the technology is the AC to AC converter, which in conjunction with the control board controls the voltage and polarity across this control winding, and that provides the sub-cycle regulation. So as we impress a voltage on this winding, it is reflected onto the secondary, and it either adds or subtracts voltage to the each of the two hot phases coming in, which pass directly through these windings and out. So the regulator can be bypassed with the external switch here, which shorts this winding out and lets the regulator continue to supply power to the customer, but there's just no regulation. There's an external LED that's used as the first line user interface. So if the LED is on, the regulator is functioning and regulating, and if it's blinking, it's in a fault condition. And if the LED is out, that means the control board has had a failure or one of these fuses has blown. This is what it looks like inside. This is the converter board that we talked about. This is the standing up here perpendicularly is the control board, which tells the converter board what to do. This is the series injection transformer. These are MOVs provided for transient protection. These are the EMI filters, and these two devices are input and output inductors. All of this is provided in a very compact and lightweight enclosure, especially considering it has a 50 kVA rating. This is the efficiency curve of the regulator, and you can see that it very rapidly exceeds 99% efficiency. For the most part, the regulator operates in this range where the efficiency is in excess of 99.5%. This is an alternative way to plot efficiency. Here we're plotting losses as a function of the load current, and the losses are typically less than half of 1% of the load current. The regulator itself, with no load, draws about 32 watts of power. It's extremely efficient, and it appears as a 0.5 kVA capacitive load to the network. The LVR50 is designed to match a 50 kVA transformer in terms of overload capacity, and this graph defines the operating parameters as a function of the ambient temperature. It's designed to operate in a 50-degree ambient environment. So if the regulator were to run at 80% of its rated load 24 hours a day until the temperature stabilized, you could then run it at 120% of its rated load for another 6 hours if the ambient temperature is 40 degrees. Two regulators can be used to mitigate the voltage collapse on an open delta service. One regulator is typically connected to the split phase transformer, and its function is to move this point left or right. A second and significantly smaller regulator is connected between the neutral point and this point, and its function is to move that point up or down. So by coordinating the actions of these two regulators, we can move this point around in order to maintain a true equilateral triangle for delta connected loads. Lastly, I would like to describe the power interactive regulation feature, which could also be described as a bidirectional line drop compensation. This feature was developed for the Australian market, where they have the world's largest penetration of rooftop solar on their LV networks. And the black line represents the load curve on a typical LV network, and this is what's referred to as the classic duck curve. So what was going on in Australia is people would put in rooftop solar, and then they would think, well, we have this basically free energy source on our roof, so the next thing they would do is go out and install a larger air conditioning unit. So not only do they have a large amount of reverse power flow during the middle of the day, people come home at night and turn on their AC, and the peak load in the evening suddenly became 2 to, in some cases, 4 times what it had been historically and what the LV network feeder was designed to accommodate. So in order to manage these issues without spending a lot of money to rebuild the feeder, we developed this feature, and the red and the blue line represent 2 out of an infinite number of options to change the set point as a function of the power flow and direction. So in the early morning, when you have normal power flow, we reduce the, we raise the voltage. And as the power flow crosses to 0 and goes into reverse, we lower the voltage out of the regulator, and this counteracts the voltage rise from the reverse power flow on the LV network. And then towards sundown, it again transitions through the 0 point, which we call the null point, and this null point can be adjusted. It could be 240, 235. You have control over that. And as the load climbs, we raise the voltage in proportion, and that offsets the voltage drop from higher than normal power flow. So we can maintain voltage compliance on the LV networks up to the thermal limit of the feeder as it's designed. This is another way to describe this feature. The red line is the output of the regulator. The blue line is the input voltage to the regulator. The green line is the load current passing through the regulator. This black line is kilowatts. So you can see as the current rises, the output voltage is increased in proportion to the current. And here there are some current oscillations provided to illustrate the dampening effect, which you have control over. That's the time constant here. And the current then reduces, drops back to 0. The power flow is also 0 at this point. The regulator voltage drops to the null point. At this time, the power reverses. You can see we have negative power now, and as the current increases, the output voltage of the regulator decreases. So it is compensating bidirectionally for the current flow in a way that offsets the rise or fall of voltage due to the system impedance. Thank you for your time, and I appreciate your interest in Pacific Volt low voltage regulators.